Alright, it looks like I should be good. Let me just quick check that I'm actually online. Okay. Looks like stream is running. Give me a sec to just clarify something technically, make sure everything is all good. Okay. Now, before we continue, I have something from last time to do. It was a problem that I was struggling on a lot for a while last time, and I learned there's a good reason that I struggled on it. It's not exactly easy. There's a lot of computation. So I'm just gonna quick go through a derivation there. So okay, we want to prove if R is a ring such that a squared equals a for all a, then R is commutative. Then R is commutative. Alright. Now for this, I have a whole notebook set up, a whole page on it set up for the notes of this, because it's not exactly easy. So we start with this. First, we're going to obtain an identity. That's going to basically be the preface for the entire proof. So we have a plus b, a minus b. Let's work this out. This is a squared. Actually, instead of writing a squared, I'm going to write a times a plus b times a minus a times b minus b times b. So we get a squared plus ba minus ab minus b squared, which is just equal to, because of this up here, is just a plus ba minus ab minus b squared. Now, notice that since these are all equalities, this then implies that we have a plus ba minus ab. It shouldn't be b squared here. I was being dumb here. Give me a second. A plus b. Actually, no, not that. So, oh gosh, I'm just floundering around. Give me a minute to collect myself. So we have from here, ba minus ab is equal to a plus b, a minus b minus a minus b. You'll understand why I'm doing this later. From here, what we have is we multiply it on the left by a plus b. Ba minus ab is equal to a plus b squared, a minus b minus a plus b, a minus b. But because of our definition of the ring, we're going to be coming back to this fact a lot. We have that this is just equal to a plus b, a minus b, minus a plus b, a minus b, which is just equal to 0. So we're going to be able to, this will set up the commutativity we want. Because what we want to show is we want to show that this term evaluates to 0. So expanding this out gives us, is equal to a ba minus a squared b plus b squared a minus bab. So we have that aba minus a squared, no, not a squared b, minus ab plus ba minus bab is equal to 0. And from this, we have two important identities, but I'll only mention one for now. We have that ba minus ab is equal to bab minus aba. Now from here, we have, from here we can't really do much, so what we're going to instead do is just go back to this. We have ab squared minus a is equal to 0. Or no, ab squared minus ab is equal to 0. So we have ab minus ab is equal to 0. We factor out the a to get a bab minus not a, my bad, minus b is equal to 0. And from here, notice that we actually now get a new definition. We get that bab is equal to ba minus ab plus aba. So we can just replace, we can just substitute that there. So we have a ba minus ab plus aba minus b is equal to 0, which gets us that aba minus ab. Notice that we have aba, and then if we multiply, I'll just write it full out. A squared b plus a squared ba minus ab is equal to 0, which, again, coming back to this fact a ton here, gets us that aba minus ab plus aba minus ab is equal to 0, or that aba plus aba is equal to aba plus aba is equal to ab plus ab. And we are getting close to done. This problem is a ton of computations, and it's very indirect. But if we just keep this identity in mind, this is going to be an extremely important identity. So from here, we have that, using once again the standard definition, we have that ba minus ab minus ab is equal to ba minus ab. So computing this gets us ba squared minus b a squared b minus a b squared a plus ab squared is equal to b a minus ab, which is just ba minus bab minus aba plus ab is equal to ba minus ab, which gets us that we subtract the ba on that side, and then we add the ab here, the stuff here, to get that ab plus ab is equal to bab plus aba. However, notice that we can connect these two equalities right here to get that aba plus aba is equal to bab plus aba. Because we have an abelian group, we can cancel these out and cancel to solve for the fact that aba is equal to bab. However, what this means is that bab minus aba is equal to 0. But what we can do is we can bring it back around up here, because this implies that this is equal to 0. But this implies that BA minus AB is equal to 0, which implies ultimately that BA is equal to AB. Oh gosh, how long did clarifying that one detail take? Let me check. 10 minutes. Nice. Okay. But that is ultimately why the problem is so hard. There's a lot of unintuitive steps and a very unintuitive path, but you can have a path to prove commutativity. Alright, I'm just going to completely zoom out of the board if you want to check out all the details, like on this slide if it loads correctly. Alright, yeah, so basically this set of just horrible algebraic manipulations here. But anyways, time to go. Less of this, please, dear God. More reading. Alright, so we delete that. Then we go back to standard layout and standard textbook scene. Let me double check that this is working and looking right. Alright, looks like it is. Alright, so without further ado then, let's begin reading. Chapter 17, Polynomials. Wait, also let me just move this book to the side. Most people are fairly familiar with polynomials by the time they begin to study abstract algebra. When we examine polynomial expressions such as p of x equals x cubed minus 3x plus 2 and q of x equals 3x squared minus 6x plus 5, we have a pretty good idea of what px plus qx and px times qx mean. We just add and multiply polynomials as functions. That is, p plus qx equals px plus qx equals x cubed minus 3x plus 2 plus 3x squared minus 6x plus 5 equals x cubed plus 3x squared minus 9x plus 7. And pqx is equal to pxqx is equal to x cubed minus 3x plus 2 times 3x squared minus 6x plus 5 is equal to 3x to the 5 minus 6x to the 4 minus 4x cubed plus 24x squared minus 27x plus 10. It is probably no surprise that polynomials form a ring. In this chapter, we shall emphasize the algebraic structure of polynomials by studying polynomial rings. We can prove many results for polynomial rings that are similar to the theorems we proved for integers. Analogues of prime numbers, the division algorithm, and the Euclidean algorithm all exist for polynomials. And as well, I'm just going to give you a kind of preview here. Polynomials allow us to describe over a field some variable that we can't give a name to. So for example, if we define the polynomial x squared plus 1 to be like equal to 0, and we have that ideal, it can represent the fact that I squared plus 1 is equal to 0, and we can have identities based on that from polynomials. So there is way more that comes out of studying polynomials than can be initially thought. As well, talk to an algebraic geometrist. They'll definitely tell you about polynomials. But anyways. 17.1. Polynomial rings. Throughout this chapter, we shall assume that R is a commutative ring with identity. So, R is commutative with identity. So we're just assuming that. Alright. I'll also write assume for chapter. Assume for chapter. Alright. Any expression of the form f of x equals the sum from I equals 0 to n, a sub I x to the I is equal to a to the 0 plus a1x1 plus a2x2 all the way to plus an xn, where ai is in R and an is not equal to 0, is called a polynomial over R with indeterminate x. The elements a0, a1, all the way to an are called the coefficients of f. The coefficient an is called the leading coefficient. A polynomial is called monic if the leading coefficient is 1. If n is the largest non-negative integer, for which an is not equal to 0, we say that the degree of f is n, and write degree of f of x equals n. If no such n exists, that is, if f equals 0 is a 0 polynomial, then the degree of f is defined to be negative infinity. This is a subtle point, I'm not going to emphasize this too much. Just remember, negative infinity implies that we have 0 polynomial. We will denote the set of all polynomials with coefficients in a ring R by r of x. So r of x is equal to polynomials with coefficients in R. Alright, with R of x, two polynomials are equal exactly when their corresponding coefficients are equal. That is, if we let p of x equals a0 plus a1x plus all the way up to plus an of xn, and q of x equals b0 plus b1x plus all the way up to bm xm, then p of x is equal to q of x if and only if a sub I is equal to b sub I for all I greater than or equal to 0. I'm also going to say, note that this shows something really subtle. So consider like polynomials with coefficients z mod 2, right? You only have like something like 4 polynomials total that you can possibly have as functions. You don't have, because you only have 2 inputs total and you only have 2 outputs total, so at max you have 4 polynomials. And what that means is that, wait, let me think of how I want to phrase this. What that means is that this equality is more than just what the values equal. The polynomials are kind of living things in and of themselves, more so like formal combinations in terms of an indeterminate x. So like even if 2 polynomials are equal on the output as functions, we don't necessarily call them equal if the coefficients are not. Anyways, to show that the set of all polynomials form a ring, we must first define addition and multiplication. We define the sum of 2 polynomials as follows. Let p of x equals a0 plus a1x plus on plus anx, anxn, and q of x equals b0 plus b1x plus all the way on to plus bmxm. Then the sum of p of x and q of x is p of x plus q of x is equal to c0 plus c1x plus all the way on to plus ckxk, where ci is equal to a to the I plus b to the a sub I plus b sub I for each I. We define the product of p of x and q of x to be px qx equals c0 plus c1 x plus all the way on to plus c sub m plus n x to the m plus n, where ci is equal to the sum from k equals 0 to the I, ak plus bik, which is equal to a0 bi plus a1 bi minus 1 plus on to plus ai minus 1 b1 plus ai b0 for each I. Notice that in each case, some of the coefficients may be 0. Alright, this is going to go, if the book doesn't make it clear, this is the most general form of polynomial multiplication, but I'm not going to overemphasize it because it's a computational mess. You kind of just work with this definition as implied, or as needed. Alright, example 17.1. Suppose that p of x is equal to 3 plus 0x plus 0x squared plus 2x cubed plus 0x4, and q of x is equal to 2 plus 0x minus x squared plus 0x cubed plus 4x to the 4 are polynomials in zx. If the coefficients of some term of the polynomial is 0, then we usually just omit that term. In this case, we would write p of x is equal to 3 plus 2x cubed, and q of x is equal to 2 minus x squared plus 4x4, 4x to the 4. The sum of these two polynomials is p of x plus q of x equals 5 minus x squared plus 2x cubed plus 4x4, and the product p of x q of x is equal to 3 plus 2x cubed times 2 minus x squared plus 4x to the 4, which is equal to 6 minus 3x squared plus 4x cubed plus 12x to the 4 minus 2x to the 5th plus 8x to the 7th, can be calculated either by determining the CIs in the definition above, or by simply multiplying polynomials in the same way that we have always done. So yeah, what it's talking about is you can basically use the distributive law, and then you kind of just index over what that distributive law hits. And it's kind of why we have these balancing things here. Notice that the ith degree term, we have the sum of terms that are like have degree equal to 1 or equal to I here. So like this would come from the term a to the 0, b to the I. So this term right here would be like the ith term contributed by those two. This would be the first degree term and the I minus 1 degree term, so they would multiply to an ith degree term, things like that. Alright. Example 17.2. Let p of x equals 3 plus 3x cubed, and q of x is equal to 4 plus 4x squared plus 4x to the fourth be polynomials in Z mod 12x. The sum of p of x and q of x is 7 plus 4x squared plus 3x cubed plus 4x to the 4. The product of the two polynomials is the zero polynomial. This example tells us that we cannot expect r of x to be an integral domain if r is not an integral domain. Yeah, because everything here, every coefficient would be like 3 multiplied by 4. So you multiply them together and you get like the zero polynomial by even the coefficient definition. Alright, theorem 17.3. Let R be a commutative ring with identity. Then Rx is a commutative ring with identity. Proof. Our first task is to show that R of x is an abelian group under polynomial addition. The zero polynomial, f of x equals 0, is the additive identity. Given a polynomial p of x, which is equal to the sum from I equals 0 to n of a sub x, a sub I, x to the I, the inverse of p of x is easily verified to be negative p of x equals the sum from I equals 0 to n of negative a sub I, x to the I. Commutativity and associativity follow immediately from the definition of the polynomial addition and from the fact that addition in R is both commutative and associative. To show that polynomial multiplication is associative, let p of x be equal to the sum from I equals 0 to m of a sub I, x to the I, q of x equals the sum from I equals 0 to the n, b sub I, x to the I, and r of x be equal to the sum from I equals 0 to p of c sub I, x to the I. Then, oh god, this is a bad computation. You take the product, you multiply them together to get this term that you just treat as another polynomial terms with each of the coefficients. You carry this sum into here and apply the regular definition with all this here. But now you have something that varies based on 3 terms, and they're all symmetric. So you can reverse this process, unwrap it in the other direction, but instead treating it in terms of m and n minus p, instead of m plus n and p over here. I'm going to leave this on screen for a while longer, but there's nothing that really comes good out of me verbally explaining all this, because it's just one of those things where it's a simple application of the definitions. And the common associativity thing where you wind it one way, show that you have one almost larger collection that's based on something abelian, and then from that abelianness you unwind it the other way. Or, yeah, not abelianness, the associativity of what we're working with. And commonly for this, it's the associativity of the integers and the fact that the integers represent an action on something. Alright, I think that's probably enough time. So, the commutativity and distribution properties of the polynomial multiplication are proofs in a similar manner. We shall leave the proofs of these properties as an exercise. Proposition 17.4. Let p of x and q of x be polynomials in Rx, where R is an integral domain. The degree of p of x plus degree of q of x is equal to the degree of p of x times q of x. Furthermore, Rx is an integral domain. Yeah, okay. They did note here. I was about to say this seems wrong, but then they did note that is an integral domain, so that's true. Proof. Suppose that we have two non-zero polynomials, p of x equals a sub m, x to the m, plus on and on, plus a sub 1 x to the 1, plus a sub 0 x to the 0. Also note that depending on conventions, because our ring is commutative, it doesn't matter what order we put these in. So depending on the application, we'll put them in either increasing or decreasing order. And q of x be the same expression but with b's swapped out from the indices, with a sub m not equal to 0 and b sub n not equal to 0. Oh gosh. The degrees of p of x and q of x are m and n respectively. The leading term of p of x, q of x is a to the m, b to the n, x to the m plus n, which cannot be 0 since R is an integral domain. Hence the degree of p of x, q of x is m plus n, and p of x, q of x is not equal to 0. Since p of x is not equal to 0, and q of x not equal to 0, imply that p of x, q of x not equal to 0, we know that R of x must also be an integral domain. We also want to consider polynomials in 2 or more variables, such as x squared minus 3xy plus 2y cubed. Let R be a ring, and suppose that we are given 2 indeterminates x and y. Certainly we can form the ring R of x, y. It is straightforward, but perhaps tedious, to show that R of x, y is isomorphic to R of y, x. We shall identify these 2 rings by the isomorphism, and simply write R of x, y. So I'm going to just write that here. So r of x y is defined to be r of xy. We also, in this case, the ring R of xy is called the ring of polynomials in two indeterminates x and y with coefficients in R. We shall also define the ring of polynomials in n indeterminates with coefficients in R similarly. We shall denote this ring by R of x1, x2, all the way to xn. Note something important here. Note these square brackets. So what we commonly have is, in a lot of literature, we'll also have R of xy written like this, which will be, basically it allows expressions such as xy squared, but also 1 over xy to xy cubed minus x squared over 2y. It basically allows for field operations on this if we have the round brackets. But when we have the square brackets, it's just the normal polynomials like we're used to. Theorem 17.5. Let R be a commutative ring with identity, and alpha be an element in R. Then we have a ring homomorphism, phi of A from R of x to R, defined by phi of A, p of x equals p of A equals an A to the n, all the way to plus A1 alpha plus A0, where p of x is equal to A sub n, x to the n, plus on and on. So basically, it's called the evaluation homomorphism. It literally says that later. And what we have is a polynomial is a function, right? And this homomorphism takes it to the evaluation of that function on that input. So proof. Let p of x be equal to the sum from I equals 0 to n, a sub I x to the I, and q of x be equal to the sum from I equals 0 to the m, b sub I x to the I. It is easy to show that phi a px plus qx is equal to phi a px plus phi a qx. To show that multiplication is preserved under the map phi a, observe that phi a px phi a qx is equal to p a qi equals the sum from I equals 0 to m, a sub I alpha I, times sum from I equals 0 to m, b sub I alpha I, is equal to the sum from I equals 0 to m plus n, times the sum from k equals 0 to I, a sub k, b sub I minus k, alpha to the I, which is equal to phi of a, p of x, q of x. It's just a fancy way of saying that multiplication works as expected. The map phi a from Rx to R is called the evaluation homomorphism at A. The division algorithm. Recall that the division algorithm for integers says that if a and b are integers with b greater than 0, then there exist unique integers q and r such that a equals bq plus r, where 0 is less than or equal to r is less than b. The algorithm by which q and r are found is just long division. A similar theorem exists for polynomials. The division algorithm for polynomials has several important consequences. Since its proof is very similar to the corresponding proof for integers, it is worthwhile to review theorem 2.9 at this point, which we're not going to do. I already have a previous video if you want to check out the division algorithm there. Theorem 17.6, division algorithm. Let f of x and g of x be polynomials in fx, where f is a field, note here, I'm going to just emphasize it over and over again, and g of x is a non-zero polynomial. Then there exist unique polynomials q of x, r of x in f of x, such that f of x is equal to g of x q of x plus r of x, where either degree of r of x is less than degree of g of x, or r of x is the zero polynomial. So proof. We will first consider the existence of q of x and r of x. If f is a zero polynomial, then 0 is equal to 0 times g of x plus 0. Hence, both q and r must be the zero polynomial. Now, suppose that f of x is not the zero polynomial, and that degree of fx equals n, and degree of g of x equals m. If m is greater than n, then we can let q of x equals 0, and rx equals f of x. Hence, we may assume that m is less than or equal to n, and proceed by induction on n. If f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 on and on to a sub 0, and g of x is defined similarly, but we both begin at b and use the indexing of b's instead of a's, the polynomial f prime of x equals f of x minus a sub n over b sub m, x to the n minus m g of x has degree less than n, or is the zero polynomial? So there's something, that's degree less than n. Yes, looks right. So I will note here that we need the field assumption here. We need the field assumption here. And f of x, f prime of x in this case is not referring to a derivative. They start using this and they start doing casual notation that like they do this to get you more comfortable with it, because a lot of times we'll just use primes for alternative expressions derived from stuff, not for derivatives. So just want to put that note there. So the polynomial f prime has degree less than n, or is a zero polynomial. By induction, there exist polynomials q prime in x and r of x such that f prime of x equals q prime x g of x plus r of x, where r of x is equal to 0, or the degree of r of x is less than the degree of g of x. Now, let q of x equal q prime of x plus an over bm x to the n minus m. Then f of x is equal to g of x q of x plus r of x. So let me just like make sure I'm fully convinced of this. So we define f prime of that. So g of x q of x plus r of x. Yes, that looks right. That looks right. With r of x is zero polynomial, or with r of x is zero polynomial, or degree r of x less than the degree of g of x. To show that q of x and r of x are unique, remember we just constructed these, we didn't show that they were unique yet. Suppose there exist two other polynomials, q1 of x and r1 of x, such that f of x equals g of x q1x plus r1x with degree of r1x less than the degree of g of x, or r1x equals 0. So that f of x equals gx qx plus rx equals g of x q1 of x plus r1 of x. And g of x minus g1 of x, g of x qx minus q1 of x is equal to r1x minus r of x. If qx minus q1x is not the zero polynomial, then the degree of g of x q of x minus q1 of x is equal to the degree of r1 of x minus r of x is greater than or equal to the degree of g of x. However, the degrees of both r of x and r1x are strictly less than the degrees of g of x. Therefore, rx is equal to r1x and qx is equal to q1x. Oh, that's very clever. That's very clever. I like that. I like that. That's a nice proof. Alright. Example 17.7. The division algorithm merely formalizes the long division of polynomials, a task we have been familiar since high school. For example, suppose that we divide x cubed minus x squared plus 2x minus 3 by x minus 2. I never learned to divide polynomials like this. I learned to divide polynomials by another method, because my teachers were like crap in like late middle and early high school. So I have no idea what this notation means, and I'm not going to worry about it. Hence, x cubed minus x squared plus 2x minus 3 is equal to x minus 2, x squared plus x plus 4 plus 5. Let p of x be a polynomial in f of x, and alpha in f. We say that alpha is a 0 or root of p of x, if p of x is in the kernel of the evaluation homomorphism phi of f. All we are really saying here is that alpha is a 0 of p of x, if p of alpha is equal to 0. Yeah, that makes sense. That makes sense. Yeah, okay. Oh gosh, why is it lagging so badly? Oh, this is particularly unfortunate. Corollary 17.8. Let f be a field. An element alpha in f is a 0 of p of x in f of x, if and only if x minus a is a factor of p of x in f of x. Proof. Suppose that alpha is in f, and p of alpha is equal to 0. By the division algorithm, there exist polynomials q of x and r of x, such that p of x is equal to x minus alpha, q of x, plus r of x. And the degree of r of x must be less than the degree of x minus alpha. Since the degree of r of x is less than 1, rx is equal to a for a in f. Therefore, p of x is equal to x minus alpha, q of x plus a. But 0 is equal to p of alpha is equal to 0 times q of alpha plus a is equal to a. Consequently, p of x is equal to x minus a q of x, and x minus a is a factor of p of x. Oh, that's nice. That's really nice, actually. Conversely, suppose that x minus alpha is a factor of p of x. Say px equals x minus a q of x. And then p alpha is equal to 0 times q of alpha is equal to 0. So corollary 17.9. Let f be a field. Note here the importance of fields here. A non-zero polynomial p of x of degree n in f of x can have at most n distinct zeros in f. And remember, a fundamental theorem of algebra is that we have n possibly non-distinct zeros. This is just saying that we can have at most n distinct zeros, so this is an upper bound. So proof. We will use induction on the degree of p of x. Oh wait, give me a sec to make sure things are working technically alright. Okay, it is. Alright, well, the degree of p of x, yeah, okay. Wait, what am I doing? Okay, we'll use induction on the degree of p of x. If degree of p of x is equal to 0, then p of x is a constant polynomial and has no zeros. Let degree of p of x equal 1. Then degree, no, wait, okay. Oh wait, yeah, because the zero polynomial has degree negative infinity, so you can't do the standard induction. So let degree of p of x equal 1. Then p of x is equal to ax plus b for some a and b in f. If a1 and a2 are zeros of p of x, then a alpha 1 plus b is equal to a alpha 2 plus b, or a1 is our alpha 1 is equal to alpha 2. So it shows that any zeros above that, when you have that degree, are unique. Now, assume that degree of p of x is greater than 1. If p of x does not have a 0 in f, then we are done. On the other hand, if alpha is a 0 of p of x, then p of x equal x minus alpha q of x for some q of x and f of x by corollary 17.8. The degree of q of x is n minus 1 by proposition 17.4. Let beta be some other 0 of p of x that is distinct from alpha. Then p of beta is equal to beta minus alpha, q of beta is equals 0. Since alpha is not equal to beta, and f is a field, note field also means integral domain, q of beta is equal to 0. By our inductive hypothesis, q of x can have at most n minus 1 zeros in f that are distinct from a. Therefore, p of x has at most n distinct zeros in f. So now, let f be a field. A monic polynomial dx is a greatest common divisor of polynomials p of x, q of x, and f of x if d of x evenly divides both p of x and q of x, and if for any other polynomial d prime of x dividing both p of x and q of x, d prime of x divides d of x. We write d of x is equal to the GCD of p of x, q of x. Two polynomials p of x and q of x are relatively prime if the greatest common divisor of p of x, q of x is equal to 1. A lot of this more so comes down to the roots from the looks of it. At least in the nice case where you can like turn any polynomial into a multiplication of roots. It's still not exactly fun though. Anyways. Proposition 17.10. Let f be a field and suppose that d of x is the greatest common divisor of two polynomials p of x and q of x and f of x. Then there exist polynomials in r of x and s of x, such that d of x is equal to rx px plus xx qx. Furthermore, the greatest common divisor of two polynomials is unique. So this is basically saying that, how do I phrase this? My brain's not working. So it's basically the analogy of the case for greatest common divisor of two numbers into the realm of polynomials. So anyways, proof. Let d of x be the monic polynomial of smallest degree in the set S equals fx p of x plus qx gx qx in f of x, g of x, and f of x. Be the monic polynomial. Yeah, because of how they sum together. And because we have a field, we're able to ensure that that's the like smallest degree. Okay, and we're able to ensure it's the monic polynomial smallest degree. Okay. We can write d of x is equal to r of x p of x plus s of x q of x for two polynomials r of x and s of x in f of x. We need to show that d of x divides both p of x and q of x. We first show that d of x divides p of x. By the division algorithm, there exist polynomials a and x and b of x such that px is equal to ax dx plus bx, where bx is either the two polynomials or degree of b of x is less than degree of d of x. Therefore, b of x is equal to p of x minus a of x d of x is equal to p of x minus a of x r of x p of x plus s of x q of x. is equal to p of x minus a of x, r of x, p of x, minus a of x, s of x, q of x, is equal to p of x, 1 minus a of x, r of x, plus q of x, negative a of x, s of x, is a linear combination of p of x and q of x, and therefore must be an S. However, b of x must be the zero polynomial, since d of x was chosen to be of smallest degree. Consequently, d of x divides p of x. A symmetric argument shows that d of x must also divide q of x. Hence, d of x is a greatest common divisor of p of x and q of x. To show that d of x is a greatest common divisor, not a greatest, it's just a common. To show that d of x is the greatest common divisor of p of x and q of x, suppose that d prime of x is another common divisor of p of x and q of x. We will show that d prime of x divides d of x. Since d prime of x is a common divisor of p of x and q of x, there exist polynomials u of x and v of x, such that p of x is equal to u of x d prime of x, and q of x equals v of x d prime of x. Therefore, d of x is equal to r of x p of x plus s of x q of x, which is equal to r of x u of x d prime of x plus s of x v of x d prime of x, is equal to d prime of x, r of x u of x plus s of x v of x. Since d prime of x divides d of x is a greatest common divisor of p of x and q of x. Finally, we must show that the greatest common divisor of p of x and q of x is unique. Suppose that d prime of x is another greatest common divisor of p of x and q of x. We have just shown that there exist polynomials u and v in f of x, such that d of x is equal to d prime of x, r of x u of x plus s of x v of x. Since degree of d of x is equal to the degree of d prime of x is equal plus the degree of r of x u of x plus s of x v of x, and d of x and d prime of x are both greatest common divisors, degree of d of x is equal to the degree of d prime of x. Since d of x and d prime of x are both monic polynomials of the same degree, it must be the case that d of x is equal to d prime of x. My god, that's a lot. Okay. Notice the similarity between the proof of proposition 17.10 and the proof of theorem 2.10. 17.3. Irreducible polynomials. A non-constant polynomial f of x and f of x is irreducible over a field f if f cannot be expressed as the product of two polynomials g of x and h of x and f of x, where the degrees of g of x and h of x are both smaller than the degrees of f of x. Irreducible polynomials function as the prime numbers of polynomial rings. I was about to write some examples, but it looks like the book's about to go over some. Example 17.11. The polynomial x squared minus 2 in q of x is irreducible, since it cannot be factored any further over the rational numbers. Similarly, x squared plus 1 is irreducible over the real numbers. So notice here, this is kind of a prelude to, like, if we assume that there are things that this factors into, this in an extent extends the ring that we're working over. This extends it to the complex. This extends it to, well, I would say the irrationals, but just the square root of 2 in that case. Example 17.12. The polynomial p of x equals x cubed plus x squared plus 2 is irreducible over z3 of x. Suppose that this polynomial was reducible over z3 of x. By the division algorithm, there would have to be a factor of the form x minus a, where a is some element in z3 of x. Hence, it would be true that p of a is equal to 0. However, p of 0 equals 2, p of 1 equals 1, and p of 2 equals 2. Therefore, p of x has no zeros in z sub 3 and must be irreducible. Oh man. Alright, lemma 17.13. Let p of x be in q of x. Then, p of x is equal to r over s, a naught plus a1x plus all the way on to plus anx, where r, s, a naught all the way to an are integers, the ai's are relatively prime, and r and s are relatively prime. Proof. Suppose that p of x is equal to b naught over c naught plus b1 over c1x plus all the way on to plus bn over cn x to the n, where the bi's and the ci's are integers. We can rewrite p of x as p of x is equal to 1 over c naught on and on times cn times d naught plus d1 of x plus on and on to plus dn x to the n, where d naught and dn are integers. Let d be the greatest common divisor of d naught and d all the way up to dn. Then, p of x is equal to d over c naught all the way up to cn of a naught plus a1x plus all the way on to plus an xn, where di is equal to dai, and the ai's are relatively prime. Reducing d over c naught all the way to cn to its lowest terms, we can write p of x is equal to r over s, a naught plus a1x plus all the way on to plus a n x to the n, where the GCD is equal of r, wait, my bad, where the greatest common divisor of r of s is equal to 1. This theorem, okay. Theorem 17.14, Gauss's lemma. Let p of x and z of x be a monic polynomial such that p of x factors into a product of two polynomials alpha x and beta x in q of x, where the degrees of both a of x and beta of x are less than the degree of p of x. Then p of x is equal to alpha x b of x, or equal to a of x b of x, where a of x and b of x are monic polynomials in zx, with degree of alpha x equal to degree of a of x, and degree of beta of x is equal to degree of b of x. So what it's basically saying is that if we have two monic polynomials and they split over the rationals, then they also split over the integers. So in any so we can functionally move the rational case to the integer case when we have integer coefficients to start with. Proof. By lemma 17.13, we can assume that alpha x is equal to c1 over d1, a naught plus a1x plus all the way on to plus amxm, is equal to c1 over d1 alpha 1x, and beta x is equal to c2 over d2, b naught plus b1x plus all the way on to plus bn x to the n, is equal to c2 over d2 beta 1 x, where the alpha i's are relatively prime and the beta i's are relatively prime. Consequently, p of x is equal to alpha x beta x is equal to c1 c2 over d1 d2 alpha 1x beta 1x is equal to c over d alpha 1 x beta 1x, where c over d is the product of c1 d1 and c2 d2 expressed in lowest terms. Hence, dp of x is equal to c a of a1x b1 of x. That is definitely some notation right there. If d is equal to 1, then c am bm is equal to 1, since p of x is a monic polynomial. Hence, either c is equal to 1 or c is equal to negative 1. If c is equal to 1, then either am is equal to bn is equal to 1, or am is equal to bn is equal to negative 1. In the first case, p of x is equal to alpha 1x beta 1x, where alpha 1 and x and beta 1x are monic polynomials with degree alpha x is equal to degree of alpha 1x, and degree of beta x is equal to the degree of beta 1x. In the second case, ax equals negative alpha 1x and bx equals negative 1 beta 1x, which are the correct monic polynomials, since p of x equals negative a1x, negative b1x is equal to ax bx. The case in which c is equal to negative 1 can be handled similarly. Now, suppose that d is not equal to 1. Since the greatest common divisor of c and d is equal to 1, there exists a prime p such that p divides d and p does not divide c. Also, since the coefficients of a1x are relatively prime, there exists a coefficient ai such that p does not divide ai. Similarly, there exists a similar coefficient of b sub j of b beta 1x, such that p does not divide beta j. Let alpha 1 prime x and beta 1 prime x be the polynomials in z sub px, obtained by reducing the coefficients of a1x and beta 1x modulo p. Since p divides d, alpha 1 prime x beta 1 prime x equals 0 in z p of x. However, this is impossible, since neither a1 prime x nor beta 1 prime x is a zero polynomial, and z sub px is an integral domain. Therefore, d is equal to 1, and the theorem is proven. Oh my gosh, that is definitely a lemma. Okay, that's extraordinarily technical. But it's very nice, because it allows us to reduce monic polynomials that factor into things and push it back down to the integer case. And the integer case is just way easier to work with. So continuing. Corollary 17.15. Let p of x be equal to x to the n plus a sub n minus 1 x to the n minus 1 plus on and on to plus a naught be a polynomial with coefficients in z and a naught not equal to 0. If p of x has a 0 in q, then p of x also has a 0 in z. Furthermore, a divides a naught. Proof. Let p of x have a 0 a in q, then p of x must have a linear factor x minus a. By Gauss's lemma, p of x is a factorization with the linear factor in z of x. Hence, for some alpha in z, p of x equals x minus alpha times x to the n minus 1 plus on and on minus alpha naught over alpha. Thus, alpha naught over alpha is in z, so alpha divides alpha naught. Oh my gosh, okay. Example 17.16. Let p of x be equal to x to the fourth minus 2x cubed plus x plus 1. We shall show that p of x is irreducible over q of x. Assume that p of x is reducible. Then either p of x is a linear factor, say p of x is equal to x minus alpha q of x, where q of x is a polynomial of degree 3, or p of x is two quadratic factors. If p of x is a linear factor in q of x, then it must have a 0 in z. By corollary 17.15, any 0 must divide 1, and therefore must be plus minus 1. However, p1 is equal to 1, and p negative 1 is equal to 3. Consequently, we have eliminated the possibility that p of x has any linear factors. Therefore, if p of x is reducible, it must factor into two quadratic polynomials. Say px equals x squared plus ax plus b, x squared equals x squared plus cx plus d, is equal to x to the fourth plus a plus c x cubed plus ac plus b plus d, x squared plus ad plus bcx plus bd, where each factor in z is in z of x by Gauss's lemma. Hence, a plus c is equal to minus 2, ac plus b plus d is equal to 0, ad plus bc is equal to 1, and bd is equal to 1. Since bd is equal to 1, either b is equal to d is equal to 1, or b is equal to d is equal to minus 1. In either case, b is equal to d, and so ad plus bc is equal to ba plus c is equal to 1. Since a plus c equals negative 2, we know that negative 2b is equal to 1, and this is impossible since b is an integer. Therefore, p of x must be irreducible over q. Whew, that is a very powerful theorem. That's good. That's good stuff. Theorem 17.17. I'm not going to accidentally say Einstein's because it's Eisenstein's criterion. Let p be a prime, and suppose that fx is equal to an xn plus on and on to plus a naught in zx. If p divides a sub I for I equals 0, 1, all the way to n minus 1, but p does not divide a sub n, and p squared does not divide a naught, then f of x is irreducible over q. Whoa, that's powerful, okay. Proof. By Gauss's lemma, we need only show that f of x does not factor into polynomials of lower degree in z of x. Let f of x be equal to br xr plus all the way to b naught times cs xs plus all the way on to c naught be a factorization z of x, with br and cs not equal to 0 and r s less than n. Since p squared does not divide a naught equals b naught c naught, either b naught or c naught is not divisible by p. Suppose that p does not divide b naught and p divides c naught. Since p does not divide a sub n, and a sub n is equal to b sub r c sub s, neither b sub r nor c sub s is divisible by p. Let m be the smallest value of k such that p does not divide c sub k. Then a sub m is equal to b naught cm plus b1 cm minus 1 plus on and on plus bm c naught is not divisible by p, since each term on the right hand side of the equation is divisible by p except for b naught cm. Therefore, m equals n since a sub I is divisible by p for m less than n. Hence, f of x cannot be factored into polynomials of lower degree, and therefore must be irreducible. I'm definitely reading over all the Gauss's lemma and Eisenstein's criterion and stuff again, because there's a lot of details and I'm picking it up, but like that's a lot of things to take stock of. Alright, example 17.18. The polynomial f of x is equal to 16x to the fifth minus 9x to the fourth plus 3x squared plus 6x minus 21 is easily seen to be irreducible over q by Eisenstein's criterion if we let p equals 3. Eisenstein's criterion is more useful in constructing the irreducible polynomials of certain degree over q than determining the irreducibility of an arbitrary polynomial in q of x. Given an arbitrary polynomial, it is not very likely that we can apply Eisenstein's criterion. The real value of theorem 17.17 is that we now have an easy method of generating irreducible polynomials of any degree. So we can see that any degree, minus the monic term, has a irreducible polynomial related to it, which is extremely powerful. Ideals in f of x. Let f be a field. Recall that a principal ideal in fx is an ideal p of x generated by some polynomial p of x. That is, p of x is equal to p of x q of x, such that q of x is an f of x. Example 17.19. The polynomial x squared in f of x generates the ideal x squared consisting of all polynomials with no constant term or term of degree 1. Theorem 17.20. If f is a field, then every ideal in f of x is a principal ideal. Oh, this is spicy. I like this. Let I be an ideal in f of x. If I is a zero ideal, the theorem is easily seen to be true. Suppose that I is a non-trivial ideal in f of x, and let p of x and I be a non-zero element of minimal degree. If degree of p of x is equal to 0, then p of x is a non-zero constant polynomial, and 1 must be an I. Since one generates all of f of x, the principal ideal of 1 is equal to I is equal to f of x, and I is again a principal ideal. Now, assume that the degree of p of x is greater than or equal to 1, and let f of x be any element in I. By the division algorithm, there exists q of x and r of x and f of x, such that f of x is equal to p of x q of x plus r of x, and degree of r of x is less than degree of p of x. Since f of x, p of x is an I, and I is an ideal, Rx is equal to f of x minus p of x q of x is also an I. However, since we chose p of x to be a minimal degree, r of x must be the zero polynomial. Since we can write any element f of x and I as px qx for some qx in f of x, it must be the case that I is equal to the principal ideal generated by p of x. Oh gosh. This ends up being a very powerful, like very, 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 very powerful theorem. Which basically gives us near complete control of the single variable polynomials. But as we're about to see, like there's everything in algebraic geometry still to research. So example 17.21. It is not the case that every ideal in the ring f of... Wait, give me a second. My apologies for that. So continuing. Example 17.21. It is not the case that every ideal in the ring f of xy is a principal ideal. Consider the ideal f of xy generated by the polynomials x and y. This is the ideal of f of xy consisting of all polynomials with no constant terms. Since both x and y are in the ideal, no single polynomial can generate the entire ideal. Theorem 17.22. Let f be a field and suppose that p of x is in f of x. Then the ideal generated by p of x is maximal if and only if p of x is irreducible. Proof. Suppose that p of x generates a maximal ideal on f of x. Then the principal ideal of p of x is also a prime ideal of f of x. Since the maximalist ideal must be properly contained inside f of x, p of x cannot be a constant polynomial. Let us assume that p of x factors into two unique polynomials, Let us assume that p of x factors into two polynomials of lesser degree. Say p of x is equal to f of x g of x. Since p of x is a prime ideal over one of these factors, say f of x is in p of x and therefore is a multiple of p of x. But this would imply that the principal ideal of p of x is a subset of the principal ideal of f of x, which is impossible since p of x is maximal. Conversely, suppose that p of x is irreducible over f of x. Let I be an ideal in f of x containing the ideal generated by p of x. By theorem 17.20, I is a principal ideal. Hence, I is equal to the principal ideal of f of x for some f of x and f of x. Since p of x is an I, it must be the case that p of x is equal to f of x g of x for some g of x and f of x. However, p of x is p of x is irreducible. Hence, either f of x or g of x is a constant polynomial. If f of x is a constant, then I is equal to f of x and we are done. If g of x is a constant, then f of x is a constant multiple of I, and I is equal to the principal ideal generated by p of x. Thus, there are no proper ideals of f of x that properly contain the ideal generated by p of x. Sage. No. We're not doing Sage, not today. So historical note. Oh, this is fun. Throughout history, the solution of polynomial equations has been a challenging problem. The Babylonians knew how to solve the equation ax squared plus bx plus c equals 0. Omar Khayyam, I hope that's how you pronounce it, devised methods of solving cubic equations through the use of geometric constructions and conic sections. The algebraic solutions of the general cubic ax cubed plus bx squared plus cx plus d equals 0 was not discovered until the 16th century. An Italian mathematician, Luca Pacioli, wrote in Summa de Arithmetica that the solution of the cubic was impossible. This was taken as a challenge by the rest of the mathematical community. Scipione del Ferro at the University of Bologna solved the depressed cubic, ax cubed plus cx plus d equals 0. He kept his solution an absolute secret. This may seem surprising today, where mathematicians are usually very eager to publish their results, but in the days of the Italian Renaissance, secrecy was customary. Academic appointments were not easy to secure and depended on the ability to prevail in public contest. Such challenges could be issued at any time. Consequently, any major new discovery was a valuable weapon in such a contest. If an opponent presented a list of problems to be solved, Del Ferro could in turn present a list of depressed cubics. He kept the secrets of his discovery throughout his life, passing on only on his deathbed to his student Antonio Fiore. Although Fiore was not the equal of his teacher, he immediately issued a challenge to Niccolo Fontana. Fontana was known as funny enough, I keep stuttering. He was known as the Stammerer. As a youth, he had suffered a blow from the sword of a French soldier during an attack on his village. He survived the savage wound, but his speech was permanently impaired. Tartaglia sent Fiore a list of 30 various mathematical problems. Fiore countered by sending Tartaglia a list of 30 depressed cubics. Tartaglia would either solve all 30 of the problems or absolutely fail. After much effort, Tartaglia finally succeeded in solving the depressed cubic and defeated Fiore, who faded into obscurity. At this point, another mathematician, Girolamo Cardano, entered the story. Oh god, I'm gonna mispronounce this so bad. Cardano wrote to Tartaglia, begging him for the solution to the depressed cubic. Tartaglia refused several of his requests, then finally revealed the solution to Cardano after the latter swore an oath not to publish the secret or to pass it on to anyone else. Using the knowledge that he obtained from Tartaglia, Cardano eventually solved the general cubic ax cubed plus bx squared plus cx plus d equals 0. Cardano shared the secret with his student, Ludovico Ferrari, who solved the general quartic equation ax to the fourth plus bx cubed plus cx squared plus dx plus e equals 0. In 1543, Cardano and Ferrari examined Del Ferro's papers and discovered that he had also solved the depressed cubic. Cardano felt that this relieved him of his obligation to Tartaglia, so he proceeded to publish the solution in Ars Magna, in which he gave credit to Del Ferro for solving the special case of the cubic. This resulted in a bitter dispute between Cardano and Tartaglia, who published the story of the oath a year later. Oh my gosh. That was a horrible mispronunciation of names. Okay, so reading questions. Suppose p of x is a polynomial of degree n with coefficients from any field. How many roots can p of x have? How does this generalize your high school algebra experience? It can have at most n roots for being a degree n polynomial. 2. What is the definition of an irreducible polynomial? Given a field f, an irreducible polynomial is a polynomial that cannot be written as the product of non-constant polynomials other than of degree greater than 0 and strictly less than n. Yeah. Find the remainder upon... No. A single theorem in this chapter connects many of the ideas of this chapter, many ideas of the previous chapter. State a paraphrased version of this theorem. The division algorithm. I'll just say that. Early in this chapter, we say we can prove many results for polynomial rings that are similar to the theorems we proved for the integers. Write a short essay or a very long paragraph justifying this assertion. Nah, I'm good. Is this the strangest way to go to intermission time? I think it might be. Alright, I'm back and I think I'm ready to go. So switching scenes. Boom. Okay, that's the correct scene, right? Yeah. Alright, so list all the polynomials degree 3 or lower in Z mod 2. I think I'm good. So like we have our constant polynomial 0 and 1. We have 1. We have x. We have x plus 1. We have x squared. We have x squared plus 1. No, x squared plus x. X squared plus 1. And x squared plus x. X plus 1. So 2 to the 3 choices for polynomials. Compute the following. Nah, I'm good. Use the division algorithm. Nah, I'm good. The thing is, I want to work like theoretic questions, especially because I know a lot of this should just be like review, and a lot of it is review. But like I want to, if anyone's learning this, a lot of it is, I'll leave this on the screen for a little bit longer. I would suggest doing these problems just to like double check your intuition, especially with how certain stuff is eliminated in those examples. Okay. Advisor, the zeros. Find all the units of z of x. Alright, so suppose we have a polynomial in z of x. Well, because z of x is an integral domain, we know that the degree of p of x, q of x is going to be equal to degree of p of x plus degree of q of x. Degree of q of x. So because of this, and we know that the constant function, which I'll just call 1, has degree 0. Then this means that the only possible the only possible units could have degree 0. So we'll limit us simply to the constant functions a. As well, because of how multiplication works, the multiplication of a times b is just going to literally be equal to ab. So it already has to be a unit in order for this multiplication to work, which implies that the only units are 1 and negative 1. Alright. Find a unit p of x in z4 of x such that the degree of p of x is greater than 1. Okay, so showing that, yeah, we have degree greater than 0, greater than 1. So a unit in z4 of x. So like, I'm thinking it's going to be ax squared plus bx plus c, dx squared plus ex plus f. We multiply this together, and we get the function, alright, ad x to the 4th plus ae plus bd, x cubed plus, we have x cubed, so we want to do the x squared terms next. We have a f plus be plus cd x squared plus ax squared plus think plus bf plus ce of x plus cf. And we're working in Z mod 4, they said. Yes. In Z mod 4. So in Z mod 4, I mean, let's see, so CF is isomorphic. Do we want C of X to be congruent to 1 mod 4? Or is it mod 4? I keep forgetting. Mod 4? So either C is equal to F is equal to 1, or C is equal to F is equal to 3. So let's assume that C is equal to F is equal to 1. Let's write this here. So if C is equal to F is equal to 1, then we can reduce this top term, first of all, to A plus BE plus D is isomorphic to 0. And we want that B plus B plus E is equal to 0. So from here, I mean, if we want this to be really simple, we also want, we want A, can we let A and D be 1? We cannot let A and D be 1. So we can let A be equal to 1, right? If A is equal to 1, then we have 1 plus BE plus D is isomorphic to 0. Which means that BE plus D is isomorphic to 3 mod 4. So if B plus E is equal to 0, then we could have, could we have D be equal to 3, B be equal to, D is equal to 3, B is equal to E is equal to 2. So this gets us the polynomials x squared plus 2x plus 1 and 3x squared I was forgetting about that. Yeah, I was forgetting about some other conditions. I was just kind of being a klutz. Don't mind me. This implies as well that AE plus BD. So we have C and F defined, right? Yeah. AE plus BD is isomorphic to 0. We have that AD is isomorphic to as congruent to 0. So let's think about this. Also, did I ever go on unmute? Is my stream loading? Let me double check that. Okay, my stream is properly loading, I just forgot to unmute it on my end. Okay, let me turn that down, because my own voice is going to distract me. So 80 is 0. B. So we have B plus E is equal to this isomorphic to 0, which means that we can write B is isomorphic to 4 minus E. Yeah. Or it's congruent to 4 minus E. So we then get that a plus 4 minus e plus d is congruent to 0, which gets us that a plus 4e minus e squared, so d is congruent to 0, which is just the same because the field we're working in is a plus e squared plus d is congruent to 0. I mean, we could just, I'm thinking, could we just let b and e and b equal 0? Because, like, that's really simple compared to everything else. Yeah. I'm wondering if we just have the polynomial 2x squared plus 1. Oh yeah, wait, do we actually have an element, like a proper idempotent element? Wait, let's see. 2x squared plus 1 times 2x squared plus 1 is equal to 4x to the 4th plus 4x squared plus 4. Wow. That's really nice. So yeah, not only have we discovered... I wonder if this, like, applies... I feel like this applies more generally. Kind of. Oh, it specifically comes, yeah. So, like, it looks like... Oh, there's probably some, like, binomial coefficient you can do to always make these nilpotent elements. But yeah, that is really cool. Showing that we have an irreducible element, a reducible element of degree 2. Sick. Okay. Nah, if I know there exists a polynomial d sub 6 of degree n with more than there exists a polynomial of degree z sub 6. So actually this sounds fun. So z sub 6. Assume we have a polynomial. So it can't be a monic polynomial. That much is for sure. So let's have a quadratic polynomial. So ax squared plus bx plus c. We want this to have more than 2 zeros. So suppose, like, okay. So 1 squared is equal to 1. 2 squared is equal to 4. 3 squared is equal to... let me think properly. 3 squared is equal to 9. 9 is congruent to 3 mod 6. Oh god, idempotent element, weird. 4 squared is equal to 16. 6, 12 is equal to 2. You want to check something? Alright, okay. And then 5 squared, our last element. So 5 squared is equal to 25 is equal to 1. I wonder. So I think these look like our big breaks because they're the same. So like x squared plus bx plus c. What if we have x squared plus 5x? Right? With value 1, we have, at 1, we have, at 0, we have a 0. At 1, we have another 0. Because 1 squared plus 5 is 6. At 2, we have 4 plus 5. 4 plus 10 equals 14. 6, 12 is 2. At 3, we have 9 plus 15. Oh gosh, I should get a calculator out or something, because I am very bad with mental math. So 9 plus 15 is equal to 20. Ooh, is equal to 24, so it's equal to 0. And we've already found it. That is our polynomial. X times x, x plus 5. Oh yeah, because at value 3, it's going to be 3 times 3 plus 5, which is just 2. So the, oh, that's how you do it. Okay. It's the fact that it's not an integral domain actually allows us to find. Oh, that's actually really cool. Okay, so let's do something more general from this, because this specific computation has showed something. So suppose that like we have a ring R, not an integral domain. So which means that we can find two elements A, B, and R, two elements not equal to 0, A, B, and R, such that A, B is equal to 0. Now we define in Rx the polynomial x so let's this polynomial right here, which is just, let me actually, well yeah, we can just write it in this factorized form. X minus a minus b. Now what this is at 0, it's going to be 0. At 0, this will evaluate to 0. At a, at a minus b, it'll evaluate to 0. Oh, actually, I think as well we need a separate condition. We need also that a and a squared is not equal to 0. A squared, b squared is not equal to 0. Well, then again, if everything squared multiplies to 0, you're going to have a lot of other difficulties. But okay, a minus b is 0. And as well, a is sent to 0. Since this would evaluate on the input a, it's a minus b is equal to a times b is equal to 0. So we have a degree 2 polynomial with 3 roots. If we can ensure that a is not equal to b in that, and that ab is equal to 0. Alright, prove, disprove, there's just if f is a field, show that f of x1 all the way to xn is an integral domain. I mean, you can just look at the leading term, right? Yeah, I mean, it's pretty much just a leading term stuff. This right here. And because the field is always an integral domain, that works. Yeah, another way you can say it is that, so we have f is int domain, implies that f of x is int domain. So just by induction, we have that f of x y is int domain. We basically recursively apply the logic up there. And because we're working, notice here when it specifies it, that we have a finite number of variables here, so we can apply that recursive logic. I'm assuming this will be coming from irreducibility. Oh wait, I'm phasing out. Give me a second. Okay. Proof. xp plus a is irreducible for any a in z mod p, where p is okay. So suppose that xp plus a Wait, I'm confused. I'm assuming they don't want us to assume it's 0. Because if a is 0, then like it is reducible if I remember correctly. Not reducible in a nice way, but reducible. Actually, I forget if reducibility is defined with the 0 term. So okay. So suppose xp plus a is reducible. This would imply that there's some beta such that beta of the p plus a is equal to 0, which is the same as saying that beta of the p is congruent to a mod p. For non-zero beta. I think this is the statement of... Alright, what? Actually, okay. I'm not gonna mess with this, but I'm pretty sure this is the statement of... I really forget what it's properly called. Of, is it Lagrange's? No, it's not Lagrange. It's in the section on Lagrange's theorem. But like Fermat's little theorem or something like that. I think this does hold true. That, there is nothing that like has that. Okay. Effects of I'm good. Suppose R and S are isomorphic rings. The R of X is isomorphic to S of X. You just apply the isomorphism coefficient wise, and by bijectivity and other stuff it will work out. Let f of x let f be a field and alpha in f. If p of x is in f of x, show that pa is the remainder divided. Oh, and p of x is... Oh, okay. F be a field and a in f. P of x. The evaluation is the remainder. Okay, that makes sense. Alright. Yeah, because if we divide it by x minus a, then the remainder will be like how much more other than that, which will be our actual value at a at that point. Okay. The rational root theorem. Let p of x equals to... Oh, it's nice, but I really don't particularly care. Prove that if p of r over s is 0. You know what, we'll do it. So rational root theorem. So suppose you have a polynomial which is written in terms of integer coefficients. So a naught, or actually do they begin the listing? They begin the listing at an, okay. So we have an x to the n plus a naught x naught. And suppose that p of r over s is equal to 0. R of s 0. So let me think of how one would go about this. So p of r over s is equal to 0, which means that a n r to the, which means that the sum of a sub I r to the I s to the I is equal to 0. So we have coefficients in that. Oh gosh, let me think. My brain is starting to fail. Alright, prove that if p of r of s, the greatest common divisor of r of s, is equal to 1. So if this is the case, hey, let's think about this. If GCD of r s equals 1, that implies that this is always going to be irrational, but what else can I say? So then, okay, then we know there are integers such that ar plus bs is equal to 1. So we can write bs is equal to 1 minus ar. Oh gosh, I don't think I just don't get it. So what we want to show is that, let's think here. R divides the initial term, and S divides the ending term. So we want to show that R divides, a naught. So let's think about what it would mean if R didn't divide that initial leading term. So R doesn't divide that initial leading term. Let me think. So in our solution, we have R over S times this whole term. I'm just gonna call like chi for now. This whole term chi plus a naught is equal to 0. Now is key needs to be some integer, yes. Key is an integer on this input, because a naught is an integer. So this basically says that r of key is equal to a naught s. Or that r is equal to a naught s over key. And because r is an integer, we know that s over key needs to be an integer, which means that r divides a naught. So r will divide the initial term when expressed as the greatest common divisor. Yeah, that seems about right. Let me think. Think harder, okay. So now we need to show then that s divides the initial term. So if s doesn't divide the initial term, I think I know what it is. So if s doesn't divide the initial term, oh god. Oh god, it's unfortunate. I really want to keep going on this problem, but I'm tired. Shoot. You know what, okay. I'll post a link to the rational root theorem, because I'm really not feeling it with this. Alright, q star be the multiplicative. Prove that q star is isomorphic to the integers of x plus. Okay. So we want p over q. Alright, so p over q times p prime over q prime is equal to p prime over q prime. This is bizarre. Right, so prove that q star is isomorphic to zx. So we already know that we know that a over a is mapped to 1. Is that somewhere? Okay, let me think. We also know that a over b times b minus b over a is mapped to 1. So this corresponds to a polynomial. This corresponds to a polynomial. Is equal to 1. Oh no, it's equal to 0. Okay. Because under the addition structure. 0, 0, 0. So we, oh man. I mean, I'm wondering. So this adds, and the degrees of these add. Oh my god, this is weird. I can't even imagine the isomorphism. That's the... this is bizarre. Okay. So let me rewrite it on board. We want an isomorphism between Q star times and Z X plus. Okay, so we know that A over A is sent to 0. Not that, that's horrible notation. I mean, we have A over B is equal to negative B over A. I don't know how I feel about what I think this might be leading up to. So we have, for example, 1/2 is equal to negative 2 over 1. As polynomials. So what information does the numerator and denominator tell us? So we know that P over Q, so we know that A over B. We know that A over B corresponds to a polynomial, right? And we know that B over A corresponds to a negative polynomial. How do we determine the degrees of the polynomial? So like B over 1 is equal to AB over B. Okay. So like, okay, suppose we have some element that corresponds to the constant polynomial. Is it seriously what I think it is? Oh, that might be... Oh wait, but it's positive rationals. What? Oh man. So like let's think about let's think about some stuff here. So first of all, a over 1 like a over 1 squared equals a squared over 1 still. And similarly, 1 over a squared is equal to 1 over a squared. So let's start by mapping a over 1 okay. A over 1 is mapped to 1. Oh no, a over 1 is mapped to the constant polynomial ax naught. I mean, it seems right. And then likewise, as we have to define it, 1 over a is defined to be negative ax naught. Now we run into a bit of a problem. What if we think in terms of prime factorizations? So for example, let's realize that a p over p is going to be equal to I think I'm starting to see the trick of this. So 1 is mapped to 1. If a is mapped to p of x, a to the n is mapped to np of x. So p of x, a to the n is mapped to np of x. So since the prime factorizations are all disjoint, what if we let a over 1, let's write it as this. So we have two rules for the isomorphism. First, p over 1 to the n is equal to n times x to the p. No, that can't hold. But alright, 1 is okay. 1 is mapped to 0 in this case. Oh, actually this does hold. So, okay. Suppose we have a listing of primes. Oh, I think that's fundamentally what this is. So, first of all, list the primes in the list P1, P2, on and on. Start by sending Pi over 1 to the n is equal to n times x to the I. And likewise, note that this implies that 1 over Pi to the n. Oh, I think what this fundamentally is a restatement of the unique factors of unique factorization. Unique prime factorization. Negative n x to the I. And then simply define A over B to be equal to be mapped to, or actually, yeah, and then we just define this linearly, because so every element P over Q can be written as P1, or no, I should probably use different wordings. Q1 over 1 to the 1 I1 on and on times Q to the K over 1. And I'm starting to see the very nice thing about this. The nice thing about this is that if two primes are equal, they're going to be on the top and bottom, so that division is equal to the subtraction between them. One over, yeah. Alright, so I think from how we've described this, it's clear how this actually works. And it mainly just has to do with the fact that we have that unique prime factorization along with infinitely many primes to give us infinitely many degrees. And I think we're about to go into integral domains. I feel like they should extend similarly to them. I just don't know how exactly. Or if it would be at all nice. Oh, that is wild. Okay. Yeah, that was not what I was expecting. Because I saw this and I'm like, wait, multiplicative group of rationals to a group of additive polynomials under addition? What? Oh, that is weird that you can now consider a polynomial as being in correspondence, or a positive rational as being in correspondence with a polynomial with rational coefficients. It's just weird. Alright, cyclotonic polynomials. The polynomial, so we are going to write this as, oh, this actually does come up later on in Galois theory, so I will pay closer heed to it this time than I did that time. Vnx is equal to x to the n minus 1 over x minus 1, which is equal to x n minus 1 plus x n minus 2 on and on to plus x, or is it just plus 1? Literally, yeah, just plus 1. So we need to show that this is irreducible over the integers for any prime. It is for any prime p. So suppose that p over q is a solution for this. Then we have I, p, of x of p over q is equal to, I think I see what they did there. Yeah, so this is basically saying that the only solution to, another way to say it is that the only rational solution to xn minus 1, or xp minus 1, the only rational solution to this is 1. So first of all, wait a minute. X is irreducible for q for any prime p. Well, the thing is, x squared minus 1, that's a factorization of x plus 1, x minus 1. I don't know if that case is like special in this, because when you actually expand it out like this, yeah, okay. So it is a bit of an error, I think, in terms of how they define it. Because if n is equal to 2, I mean 2 is prime, right? But your polynomial that you end up with is just x plus 1, which is like obviously irreducible. So we're talking about odd primes here. So we want to show that, suppose we have x to the p minus 1. If xp minus 1 is equal to 0, then x to the p I mean, first of all, this has to be an integer. If it's a rational, x to the p is going to be another irrational. Yeah, if it's irrational, it's going to have to be another rational. So x, so we have that x. Actually, let me form more carefully prove that. So a over b to the p minus 1 equals 0. This is a to the p over b to the p. Alright, so we have that. A to the p irreducible for q for any prime p. So a to the p over b to the p minus 1 is equal to 0. So you want to show that this term, obviously, we don't want 1 to be included. And for all other primes, the prime will be odd, so -1 won't be included. And obviously, it won't be any other integer. So what you want to show is that this is not an int if A or B is not in Z. Prime factor solutions. There'll be some prime in the denominator that's not in the numerator. Okay, yeah, it's actually fairly simple. There's some prime in the denominator here, but it's not in the numerator. And the amount of that prime will grow in the fully simplified form, because we can always reduce to where the GCD is 1, which means that they will continue being co-prime as B is multiplied by itself P times. So it simply leads to the conclusion that I can't think. That B is A over B to the P is not an integer. So A to the B over B to the P minus 1 is not 0. So A over B must be an integer. So we consider it as just an integer. So we then consider it as just an integer A to the P minus 1. So obviously A is equal to plus minus 1 from this. But P is an odd prime, so we can't have minus 1, and we're already factoring out this plus 1 case, so it can't be plus 1. That's actually fairly nice. Phi B is reducible for any prime P. I'm just wondering what the prime... Yeah, I know the primality has to do with because of the oddity. I'm just wondering what the primality has to do with it. If I was to feel in there infinitely many... If f is a field, show that there are infinitely many irreducible polynomials in f of x. I feel like it's going to be similar to this. Oh gosh. I'm starting to fall asleep now. Oh no. It's only 5. It's only 6 in the afternoon. Now it's not time for me to sleep. Oh man, I'm just... Yeah, let me see if there's anything specifically interesting about this. Oh, there is some cool, like, intro, or at least fairly interesting exercises coming up from what I remember, so I'm not going to get stuck up on this. This should be obvious. The distributive, this sounds painful. XP minus XP distinct zeros and Z sum P for P, include the XP. Alright, calculate the kernel of D if the characteristic 0 has characteristic P. Alright. Let F be a field, show that Fx is never a field. So that would come from irreducible polynomials, I'm pretty sure. Oh wait, no, that actually just comes from the fact that it's an integral domain, actually. Right? Because if you have an integral domain, and you have some term of degree 1, then for any other non-zero polynomial, that will always have the highest degree term in there. Wasn't this before? These exercises are weird, it looks like, unless I'm just not getting something, which is very possible. Additional exercises. Okay, I'll read through the additional exercises, but I'm really not feeling this. Both because there's a lot of like technical stuff, and also I'm tired and want taquitos. So, 17.6 additional exercises. Solving the cubic and quartic equations. So solve the general cubic quadratic equation ax squared plus bx plus c equals 0 to obtain x equals negative b plus or minus the square root of b squared minus 4ac over 2y. The discriminant of the quadratic equation is delta equals b squared minus 4ac, which determines the nature of the solutions to the equations. If delta is greater than 0, the equation has 2 distinct real solutions. If delta equals 0, the equation has a single repeated root. If delta is less than 0, there are 2 distinct imaginary solutions. 2. Show that any cubic of the form x cubed plus bx squared plus cx plus d equals 0 can be reduced to the form y cubed plus py plus q equals 0 by making the substitution x equals y minus b over 3. 3. Prove that the cube roots of 1 are given by those following things, the third root of roots of unity. 4. Make the substitution y equals z minus p over 3z for y in the equation y cubed plus py plus q equals 0 and obtains two solutions for a and b for z cubed. 5. Show that the product of the solutions obtained in 4 is negative p cubed over 27, deducing that the cube root of ab equals negative p over 3. 6. Prove the possible solutions for z in 4 are given by cube root of a, omega cube root of a, omega squared cube root of a, cube root of b, omega cube root of b, and omega squared cube root of b. And use this result to show that the three possible solutions for y are omega to the I, cube root of negative q over 2, plus square root of p cubed over 27, plus q squared over 4, plus omega 2i times the cube root of negative q over 2, minus the square root of p cubed over 27, plus q squared over 4, where I equals 0, 1, 2. 7. The discriminant of the cubic equation is delta equals p cubed over 27, plus q squared over 4. Show that y cubed plus py plus q equals 0. A. If it has three roots, at least two of the roots are equal if delta is equal to 0. B. Has one real root and two conjugate imaginary roots if delta is greater than 0. C. Has three distinct real roots if delta is less than 0. Solve the following cubic equation. A. X cubed minus 4x squared plus 11x plus 30 is equal to 0. B. X cubed minus 3x plus 5 equals 0. C. X cubed minus 3x plus 2 equals 0. D. X cubed plus x plus 3 equals 0. 9. Show that the general quartic equation can be reduced to, I'm not even going to worry about that. And then this is literally just all, get the resolute quartic. And then you have a method to obtain solutions to to arbitrary quartic equations, which is painful, but it's super powerful. And the interesting fact, which is like the buildup of all this, is that this only holds up to 4. There is no general solution for 5 or greater. Alright, so yeah, I'm just like, there's not much to do because I'm really just not feeling anything else. Also, no references at the end of the chapter. That is weird for this book. But yeah, I'll just probably end for now. I don't know if I'll stream later. I need to give my voice some time to rest, if nothing else. So, thanks for tuning in. Have a nice day.